Hello everyone and welcome to this AP Chemistry virtual lesson. This is the first lesson in a series of lessons on AP Chemistry. The lessons will be presented daily, Monday through Friday. We begin today, March 25th, and this series of lessons will run through Friday, May 1st. My name is Michael Faribaugh, and I teach chemistry, AP Chemistry at Albemarle High School. Go Patriots. My school is located in Charlottesville, Virginia. Good morning to you. It is 10 o'clock in the morning where I live, which is on the East Coast of the United States. I know that there are people who are watching this video. I assume most of them are studying AP Chemistry. They may live in other parts of the US or in other countries around the world. Even though some of you may be watching this video live right now, we want to remind you that each of these lessons will be recorded and available on demand on this YouTube channel for students to watch at any time. This is a virtual lesson, and as such, it will be a different experience from what I would normally do in my own classroom. In my class, I would be able to walk around the room and check on student work. Students would be able to ask me questions during the lesson. During these virtual lessons, I will make every effort to present the information clearly, and I will give you examples and diagrams and practice problems that will hopefully help you to better understand the content and the skills in the AP Chemistry curriculum. Today's lesson will cover topic 8.1, which is an introduction to acids and bases. During today's lesson, I will pause at different times during the instruction after I have asked a question. Now, this pause will give students a chance to process what I have just asked and to think about the answer to the question. In future lessons, you may find that I have so much to present, and there may be a lot of material in a 45-minute lesson, and that I might be going too fast for you to keep up with all the information. But remember, each of these lessons is being recorded and will be available on demand. So what I'm saying is that sometimes I will be pausing to give you time to think, and there may be times in future lessons where you will need to pause the video. So for example, if you're in the middle of solving a problem and I, your teacher, start moving on to explain the answer to the problem before you are finished, feel free to pause the video to give yourself the time you need to complete the problem. And then when you're ready, you can click play to see if your answer is correct. Now, I'd like to make a few brief comments about the AP Chemistry exam for this year, 2020. For more information about AP exams, you can visit the following website, apcentral.collegeboard.org. Now, at the top of the page, you can click on the link that will give you more information about how the College Board is supporting schools that may be closed right now. And all of the details are there on the website for you to read on your own. But let me highlight a few important details. Traditional face-to-face exam administrations will not take place. Students will take a 45-minute online free response exam at home. Now, some students may want to take the exam sooner rather than later, while the content is still fresh, and other students may want more time to practice. For each AP subject, there are 2 different testing dates. The full exam schedule, specific free response question types that will be on each AP exam, and additional testing details will be available by April 3rd. Any relevant free response questions in AP Classroom will be available for digital use, so students can access all practice questions of the type that will appear on the exam. In AP Chemistry, the AP exam this year will only cover the material in units 1 through 7 from the course and exam description. Now, that being said, people watching this lesson might be asking the following question. Well, if only content from units 1 through 7 will be tested on the AP exam this year, why do the first 3 lessons that are scheduled for this week include topics 8.1, which is on acids and bases, 8.2, which is on pH and pOH of strong acids and strong bases, and 8.3, which is on weak acids and weak bases and equilibrium? Well, today, the topic that we are covering, topic 8.1, is one that colleges have asked that all AP students study, even if it is not tested on the exam in 2020. And colleges are supporting AP students this year by allowing a more flexible approach to the exam, where it will focus on a lesser amount of content than in other years. To make this relevant to your upcoming AP exam, Today, and in all lessons, we will include AP exam practice questions. And I'll be making connections today between topic 8.1 and selected topics from earlier units that will be included on the AP exam. Eventually, the full schedule of review topics for the remainder of this course will be made available to you so that you, the student, can choose which topics you want to prioritize for review and thus which virtual lessons you'll want to watch. So again, on AP Central, you can find a link to the information about these live AP review courses. And so, for example, right now, you're watching the lesson on chemistry. But as you can see, there are a variety of classes available and review on YouTube Live. All right, I'm going to begin with an overview of today's lesson. As I mentioned, in this lesson, you will learn about the following topics and skills. So the topic is 8.1, Introduction to Acids and Bases. In this lesson, we'll talk about how to calculate the values of pH and pOH. We'll talk about the Kw expression, which is the equilibrium constant for the autoionization of water. And we'll talk about what species are present in a neutral solution of water. The science practice, or the skill that goes along with this topic, is to identify an appropriate theory, definition, or mathematical relationship to solve a problem. Here are some other topics from the AP Chemistry curriculum that are relevant to today's lesson, in which you should already be familiar with. So from Unit 4, which is on chemical reactions, topic 4.8 is an introduction to acid-base reactions. So today we'll talk about how to identify a Bronsted-Lowry acid and base. We'll talk about conjugate acid-base pairs and proton transfer in an acid-base reaction. The appropriate science practice or skill describe the components of and quantitative information from models and representations that illustrate both particulate level and macroscopic level properties. Here are some other topics that are relevant to today's lesson. In Unit 7, which is on equilibrium, topic 7.9 is an introduction to Le Chatelier's principle. Identify the response of a system at equilibrium to an external stress using Le Chatelier's principle, and the appropriate science practice or skill, explain the connection between experimental results and chemical concepts, processes, or theories. Now, the specific stress we'll talk about with respect to Le Chatelier's principle is a change in temperature. So therefore, it's important that you understand from thermodynamics, which is Unit 6, endothermic and exothermic processes. So explain the relationship between experimental observations and energy changes associated with a chemical or a physical transformation. The science practice or the skill provide reasoning to justify a claim using chemical principles or laws or using mathematical justification. So as you can see, even though the official title of this lesson is 8.1, there are many other topics that are relevant to today's lesson. So let me give you an overview. We'll talk about the definition of pH and pOH today. I'll talk about the difference between the H+ ion and the hydronium ion, or H3O+. We'll talk about the reaction of water with itself, the autoionization of water, relationship between pH and pOH in a pure water sample, and then the effect of changes in temperature on the value of Kw, which is the water equilibrium constant, as well as the pH of pure water, how that can change with changes in temperature. So here I'm going to start with a warm-up problem for you, and I have pulled this problem from the 2014 AP Chemistry Free Response section. So what you're looking at on the screen is a reaction between propanoic acid and water. So it says propanoic acid is a carboxylic acid, CH3, CH2, COOH, and it reacts with water according to the equation above. Now, part A of this question is to identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. Now, while you are trying to answer this question, I'm going to go ahead and do some drawing on the screen. So I'm going to draw the formula of propanoic acid, and I'd like to highlight what is the specific structural feature about this molecule that makes it an acid. Now, so far I've drawn 5 hydrogens and 3 carbons, but we actually haven't gotten to the most important part of this molecule with respect to it being an acid. And that is this final hydrogen that's on the right. So that particular hydrogen is the hydrogen that is going to be donated. This is an acid, and it is a proton donor, or an H+ donor. Now, what is it reacting with? Well, it's going to react with a water molecule in this reaction. So I'm going to go ahead and draw a water molecule. And as you can see, the water molecule also has hydrogens. But in this particular reaction, the water is behaving as a Bronsted-Lowry base. So the acid is the proton donor. That means that the base is the proton acceptor. So in this particular example, we're looking at proton transfer, so the transfer of an H+, and it always is transferred in acid-base reactions from the acid to the base. Now, what do we have on the other side of the equation? Well, after this particular transfer has occurred, we're going to produce a molecule of water that has now accepted H+. This now becomes a polyatomic ion that has a positive charge. So that is the hydronium ion, H3O+, that you can see on the right side of the equation. And after this particular bond here breaks, then the propanoic acid will turn into the following ion. This is called the propanoate ion. So it has all of the atoms except for that final hydrogen. So the propanoate ion is considered the conjugate base. I'm just going to put CB here for short. And the hydronium ion in this case is the conjugate acid of water. All right, let's take a look at the official answers from the scoring guidelines for this question. It said identify a Bronsted-Lowry conjugate acid base pair in the reaction. Clearly label which is the acid and which is the base. So as you can see, there were 2 acceptable answers to this question. So students could either have chosen this pair, which is the propanoic acid and then the corresponding ion. Now again, don't forget, if you're writing these types of things down on your paper, don't forget to include charges. There is a difference between a molecule and a polyatomic ion, so that charge is important. And in a similar way, we have this conjugate acid base pair. Don't forget to include H3O+, include that charge. All right, well, that was an example of conjugate acid base pairs. Again, to remind you of this definition, which comes from Unit 4, Topic 4.8, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So we'll come to another problem. This will give you some more practice with conjugate acid base pairs. So what you're looking at now are 4 different examples of acid-base reactions. Each of these reactions contains a water molecule. So I'd like you to focus on the water. In each reaction, decide if water is acting as a Bronsted-Lowry acid, in other words, as a proton donor, or as a Bronsted-Lowry base. So here is one of those moments I had mentioned earlier, in which I'm going to go ahead and give you a minute. I'm going to pause, give you a chance to work on this problem. You can either just think about it and imagine what the different properties are of the water in each of the 4 reactions, or if you're writing this down, this would be a good time to try to write this answer down. So again, in each reaction, decide if water is acting as an acid or a base. All right, you might still be working on this question, and that's fine. I'm going to go ahead and start talking about the answers here. So again, if you need a little more time to process, feel free to pause the video. And the first reaction I'm going to take a look at is this one involving HCl. And many chemistry students already know that this particular chemical, which is called hydrochloric acid, is an acid. So that means that it definitely is a proton donor. You can tell it's a proton donor because on the right side of the equation, we see a chloride ion, which means that this HCl has lost H+. That H+ has been transferred to the water. And you can see the hydronium ion on the right side of the equation. So in this first example, the correct answer is that water is behaving as a proton acceptor, as a base. Now, moving on to this equation down below, we have something called NH3, which is ammonia. And you might not be sure necessarily if ammonia is an acid or a base because it does contain hydrogens. And so on its own, you might not be sure what's happening. But it turns out, as you can look on the right side of the equation, that NH3, ammonia, has been transformed into NH4+, which is the ammonium polyatomic ion. So therefore, if the NH3 has acquired H+, it must have got the H+ from the water molecule. So in this reaction, water is behaving as an acid. It is a proton donor, and the ammonia is behaving as a base, a proton acceptor. Now we come to these next two equations, and I specifically chose HCO3- for a certain reason, because just like the water molecule, HCO3-, which is also known as hydrogen carbonate or bicarbonate, this is found in baking soda, it has this property. It is amphiprotic, and just like water, it is able to behave as either an acid or a base. So when you look at these reactants, you'll notice that they are exactly the same, and yet the products are different. So in one of the reactions, water might be behaving as an acid, and then in the other reaction as a base. So let's go ahead and analyze this reaction. We can see that the hydrogen carbonate ion has been transformed into carbonic acid, H2CO3, which means it must have picked up an H+ ion, in this case, from the water. So based on the direction of the proton transfer, that makes water acting as a proton donor, so as an acid. And in our next example, the hydrogen carbonate or the bicarbonate has turned into the carbonate ion on the right, so it must have lost the H+. That was transferred to the water. So the bicarbonate is behaving as an acid, and the water, as a proton acceptor, behaves as a base. So the four correct answers to this question are right here on the screen. All right, moving on to our next practice problem. This particular problem involves concepts from units 6 and 7. We have to talk about a reaction being either endothermic or exothermic. That would be from thermodynamics in unit 6. And we are dealing with an equilibrium system. That would be unit 7. So here we have a chemical reaction between N2O4 on the left, and then we have two molecules of NO2 on the right. The chemical equation shown above represents the reversible reaction. You can see the double arrows there, in which N2O4 is converted into NO2. And the value of the equilibrium constant for this reaction, that's capital K, is equal to 0.005. Now, we're not doing any calculations with the equilibrium constant, but just note that this particular value is at 25 degrees Celsius. That's important because something is about to change. It says if the temperature of the reaction vessel is increased from 25 degrees Celsius to 100 degrees Celsius, you have to make a prediction. Do you predict that the value of K, the equilibrium constant, will decrease, will increase, or remain the same? And justify your answer. So as I mentioned, thermodynamics is important, and energy, and the fact that this could either be an exothermic or an endothermic reaction. Some of you who are very familiar with this process and deciding if something is endothermic or exothermic might be focusing on the delta H right now. The delta H is positive 58 kilojoules per mole of reaction. I'm going to ask you to ignore that delta H for just a moment, and I'm going to go ahead and just draw on the screen some structural formulas. Now, I'm not going to draw all of the complete bonding and non-bonding pairs. I'm just going to show the connectivity. So we have a molecule of N2O4. And on the right side of the equation, we have 2 molecules of NO2. And what I'd like you to do is to remember something that you may have learned already in AP chemistry, and that has to do with the energy associated with breaking and forming bonds. So as you can tell from these structural formulas, as you proceed from left to right in this particular reaction, clearly it involves we are breaking a bond. And what many chemistry students have learned in their classes is that breaking a bond is an endothermic process. So energy is absorbed in the breaking of a chemical bond. So that's your first clue if you did not have access to this delta H value. Your first clue looking at the structural formulas in that from left to right. Now, sometimes in chemical reactions, bonds are both broken and formed, but in this particular example, it's fairly certain that a bond is broken, and therefore this is an endothermic process. Of course, going back to this delta H, students who have studied the change in enthalpy will know that the delta H value for a chemical reaction or for a process, physical or chemical change, if it is positive, that's an endothermic process. And if it's negative, that's exothermic. So again, here we have another reminder, this is an endothermic process. So I'm going to go ahead and add E for energy on the left side of the equation. So energy is absorbed. Now let's take a look at the second part of this question where it says, if the temperature is increased from 25 to 100 degrees Celsius, do you predict that the value of K will decrease, increase, or remain the same? What you should know about equilibrium constants is that they are temperature dependent. So the correct answer to this question is that it's either going to increase or decrease, it will not remain the same. Now you're thinking, well, what would an increase in temperature do to the value of K? And it turns out that when you increase the temperature, that puts a stress on the equilibrium system, and the equilibrium position will respond to that stress by trying to affect a change that is related to the stress. In this case, adding more heat by raising the temperature. This reaction will shift in the endothermic direction, in this case, from left to right. And as it experiences that shift, it will favor the products, and that will increase the value of K. So the correct answer to this question, the value of K should increase when the temperature is increased. The reaction is endothermic, and an increase in temperature shifts the reaction to favor more products relative to the reactants, resulting in an increase in the value of K. Now you might think, what does this have to do with acids and bases? This sounds like this is all about thermodynamics and equilibrium. Well, here we come to the next question. A chemist has 3 different samples of pure water. Each sample is at a different temperature as shown below. So we have 3 samples of pure water. One is at 10 degrees Celsius, one's at 25 degrees Celsius, and the other is at 40 degrees Celsius. Does each of these samples of pure water have the same pH value? If yes, explain why. And if no, explain why not. So depending on how you answer that question, yes or no, you might have the ability of ignoring the next part. The next part says, if these samples do not have the same pH value, arrange them in order from lowest pH to highest pH. Now, I've already kind of given you an outline and an overview of this lesson, and you may recall that I had talked about the dependence of Kw on temperature. So I'm going to tell you, especially based on that last problem we just did involving a change in the value of K, that the Kw for water, as well as the pH, is most definitely affected by temperature. So does each sample have the same pH value? No. If no, explain why not. Temperature will affect the magnitude of the Kw, which directly affects the value of pH. But how you arrange them from lowest pH to highest pH, you may not necessarily be able to do at this point. So I'm going to skip the answer to the arrangement for a little bit later in the lesson when we can talk about the specific effect of temperature on Kw. So we'll come back to this question in a moment. What I'm going to do now is to highlight some specific things that you need to know about topic 8.1. All right, so we have a definition of pH and pOH. you can see, and these equations are also listed on the AP equations and constant sheet that you get on the AP exam, that the pH is the negative log of the hydronium concentration. Now on the equation sheet, it's actually listed like this. It's the negative log of H+. So don't be confused when you see that, because remember, we said that H+ and hydronium are going to be things that we can see on the AP exam. So that's going to be something I'll mention. They are interchangeable. Now, if you know your math and logs, you can actually rearrange the equation to solve for the concentration of H+. So the opposite, in this case, the inverse, would be 10 raised to a certain power. So in this particular case, because we have a negative log, that means that the concentration of H+, which is going to be in moles per liter, is equal to 10 raised to the minus whatever the pH value happens to be. So that's a good relationship to be able to work with that on the AP exam. All right, so the term H+ and H3O+ can be used interchangeably. So if you look at these two reactions involving hydrochloric acid, the first reaction shows the transfer of a proton to a water molecule, and it forms hydronium, H3O+, and chloride. The second reaction does not show water as a reactant, but you still get H+ and Cl-. So as far as you're concerned, H+ and hydronium are used interchangeably. And with respect to, let's say, particle diagrams, here, for example, is a water molecule. H+ would just be a single white circle. And a hydronium ion in a particle diagram would look like a water molecule with an extra hydrogen attached to it. So do not be confused if on a particle diagram you see these little symbols. Here, for example, is a sample of HX, which contains H+ and X-. Now, the blue circles represent some negative ion that goes along with the hydrogen in an acid. But the diagram on the right would be equivalent in that we have, and we're not showing actual water molecules here, but in the particle diagram, if you see H3O+, you can think of it as the equivalent of H+. All right, well, I've already mentioned that water can behave as both an acid and a base. So when I say autoionization of water, what I'm talking about is a water molecule reacting with itself. That means that one of the water molecules is going to behave as an acid. So I'm going to go ahead and put a circle around this particular H+, and I'm just going to go ahead and transfer it over to this water molecule. So we have this water molecule behaving as a proton donor, and then this water molecule behaving as a proton acceptor. You would form the hydronium ion and the hydroxide ion. So the hydronium ion would be considered the conjugate acid of water, and the hydroxide ion is considered the conjugate base of water. Now, interestingly enough, you might wonder, does this particular reaction happen very much in water? Well, it does happen, and it's a very important process, but the value of the equilibrium constant, which in this case would be the concentration of hydronium times the concentration of hydroxide, it's very, very small. Now, it's so small that we're going to go ahead and write this in scientific notation. So at room temperature, or 25 degrees Celsius, this particular value is what we call the Kw, 1 times 10 to the negative 14. Now, when I show you a symbol in brackets, that means molarity, that's concentration, that's moles per liter. Sometimes you'll see it written like this. So moles per liter, sometimes you'll see capital M, but that means the concentration of hydronium ion times the concentration of hydroxide ion. And that equals 10 to the negative 14. So in pure water, those two concentrations are the same. Earlier, I had mentioned the AP equations and constant sheet. So here I'm showing you a portion of that equation sheet right now. And you can see that here is a reference to that particular equation. So not something you have to memorize. It's definitely going to be provided for you on the AP equation sheet, but it's good to be familiar with these. And then tomorrow's lesson, which talks about pH of strong acids and strong bases, you will definitely see these equations here. And on Friday, the lesson that has to do with weak acids and weak bases, we'll focus on these equations. All right, so I'm now going to show you another particle diagram. We have a particle diagram on the left and a particle diagram on the right. The question says, which of these particle diagrams represents a sample of pure water? How can you tell? So you have to focus specifically on the H3O plus and the OH minus. So it looks like I have 1, 2, 3 particles of H3O plus, and looks like I have 1, 2, 3, 4, 5 particles of OH minus. So therefore, this particular solution is not pure water. It is a basic solution in which the concentration of hydroxide is greater than the concentration of hydronium. But on the right, if you count, you can see we have exactly 4 hydronium and 4 hydroxide. So therefore, this is classified as neutral because the concentration of H3O plus or hydronium is equal to the concentration of hydroxide. Now, many of you, if I were to ask, what is the pH of this particular solution? This is neutral, pure water. Then you would say, well, it's a pH of 7. And the official answer is we don't know, because we don't know what the temperature is. And I'll come back to that. So only at 25 degrees Celsius is the pH of water 7. Some people think that pH of 7 is what defines neutral. In fact, what defines neutral is about the concentrations of each of these ions. So if the concentration of hydronium is equal to the concentration of hydroxide, that is what makes this a neutral solution. All right, so the relationship between pH and pOH in pure water is that they are the same. Because the concentrations of hydronium and hydroxide are the same, the pH is equal to the pOH. So at 25 degrees Celsius, the pKw, which is just the negative log of the Kw, is equal to 14. So that's where we get that number. And since they're equal, then 7 plus 7 is 14. Again, all of these equations are given to you on the equation sheet. So now I want to talk about the effect of changes in temperature on the value of Kw and the pH of pure water. You may remember that I had drawn an E on the left side of the equation for that reaction in which N2O4 was converted into NO2. And that was because it was an endothermic reaction. Well, it turns out that this one is also endothermic. That means that when you raise the temperature, you are going to shift the equilibrium in a certain direction. And when you lower the temperature, you will shift the equilibrium in the opposite direction. So the value of Kw is temperature dependent, as all equilibrium constants are. And the pKw is going to be a number other than 14 when the temperature is something other than 25 degrees Celsius. All right, I'm now going to give you some guided practice. And as we do this, I'm going to switch my screen for just a moment so I can show you a calculator. So I'm going to go ahead and end this show. And what you should see is a calculator. And we have some problems involving pH and pOH and the concentration of hydronium and the concentration of hydroxide. So I'm going to go ahead and type in on my calculator the negative log of 1 times 10 to the negative 9. Now, I didn't necessarily need my calculator to do this because that was a really simple number, but just to show you the process, the negative log of the hydronium concentration gives us the pH. So in this case, if the concentration of hydronium is 10 to the minus something, then that something is what we call the pH. Now, if I want to figure out the hydroxide concentration, I could take the Kw, which is 1 times 10 to the minus 14. and I could divide by the concentration of hydronium. In this case, 1 times 10 to the negative 9. And if I did that math, I would get 10 to the negative 5. 1 times 10 to the negative 5, which is the concentration in moles per liter of hydroxide. And of course, if I did the negative log of that value, I would get a pOH of 5. So even though I did use my calculator, this particular table is filled with a bunch of relatively easy kind of mental math problems. You will certainly have access to a calculator on the AP exam, but I wanted to go ahead and just show you that you could use your calculator to do some of these calculations. Tomorrow in the lesson on topic 8.2, which is on the pH and pOH of strong acids and strong bases, you will certainly have an opportunity to do those same types of calculations. All right, so I am now going to go back to the display here. And you should be able to see the rest of the problems in this table. Okay, so on the right side of the screen, you can see the relationships between concentration of hydronium and hydroxide and the pH and pOH definitions. So I'll give you a few moments to see if you can mentally or actually on your scratch paper fill in the remaining numbers in this problem. So I'm going to give you a moment to think about and work on these next 3 rows. All right, let's take a look at the second row. We have a pH of 4. So hopefully you can see that the concentration of hydronium ion would be 10 to the minus 4. And the pOH would be 14 minus the pH. That means that the pOH would be 10. And the concentration of the hydroxide ion would be 1 times 10 to the minus 10. In our next row of the table, we are starting not with the concentration of hydronium, but rather with the concentration of hydroxide. If we take the negative log and we get 12 on our calculator, remember, 12 is not the pH, 12 would be the pOH. And the pH would be 2, since 14 minus 12 is 2. So be careful when you're solving problems that you realize whether that's a pH or a pOH, and that you can get that straight and not confuse those two quantities. In our final row of the table, if the pOH is 8, 14 minus 8 is 6, and the concentration of hydronium would be 10 to the minus 6, and the concentration of hydroxide would be 10 to the minus 8. All right, now, as promised, we're going to talk more specifically about temperature and pH, and we'll get back to that problem I showed you earlier with the 3 flasks at different temperatures of pure water. So take a moment to process the information in this table. You'll notice that we have something called the pKw. Again, that's the negative log of the Kw. So I ask you to look closely at these pKw values. Now, what happens as you go from top to bottom in this table is the temperature is increasing. Look at what happens to the value of pKw as the temperature increases. And what happens to the value of Kw as the temperature increases. So be careful that you have to realize that 10 to the minus 13 is a larger number than 10 to the minus 14. And 10 to the minus 14 is a larger number than 10 to the minus 15. So be careful that you don't confuse when something is increasing or decreasing. While the pKw's are getting smaller, the Kw values are actually getting larger. So what I have done on my calculator is I have taken 10 to the minus 14.5, 10 to the minus 14.2, and then so forth and so on. And so if you look down that far right column, you notice that the actual values of Kw are getting larger. We've seen this before in other example problems where endothermic reactions, their K increases. So it says, based on this information, is the autoionization of water an endothermic or an exothermic process? Justify your answer. So what I would hope you would recognize once you realize how to do this math is that when a K value, when an equilibrium constant increases with increasing temperature, that results in a shift according to Le Chatelier's principle. So here's what I said. The autoionization of water is an endothermic process. As the temperature of water increases, we notice that the value of pKw decreases. But more importantly, the value of Kw increases. So what does that mean? That an increase in temperature is causing a shift in this particular reaction in the endothermic direction, so from left to right, and it favors more products, and that increases the value of K. So how does this affect pH? Well, on the next slide, you can see that I'm showing you different temperatures, and we have the same pKw values I showed you on the previous slide. So now, on the previous slide, we talked about the Kw. Let's talk about pH and pOH. 14.2, half of that is 7.1. So at 20 degrees Celsius, not 25, the pH of pure water is 7.1. The pOH is not 14 minus 7.1, it's actually 14.2 minus 7.1. And as you already know, in pure water, pH and pOH are the same. So as I continue to fill out this table, here is the message that I want to send to you. When water is hotter than 25 degrees Celsius, your pH goes down. This does not mean that water becomes acidic. It just means that the Kw and of course the pH is going to change. So once you are no longer at 25 degrees Celsius, the pH of water is no longer going to be 7. So for pure water at temperatures above 25 degrees Celsius, the pH of water is actually less than 7. So remember that for our follow-up to this question I showed you earlier with the 3 flasks. And at temperatures below 25 degrees Celsius, the pH of water is greater than 7. However, we are not changing the neutrality of water. Pure water is still neutral because pH equals pOH. So let's go ahead and return to this question. A chemist has 3 different samples of pure water. Does each sample have the same pH? We already said that answer was no, because the temperature changes, Kw changes, and so does the pH. So how can we arrange these values from lowest to highest pH? Well, if you remember from what I showed you on the previous slide, hot water actually has a lower pH than room temperature water. So the correct answer to this question about how to arrange them is like this. The 40 degrees Celsius water would actually be the lowest pH, and the 10 degrees Celsius water would be the highest pH. A student heats a sample of pure water to a temperature of 50 degrees Celsius and records the pH as 6.6. What is the value of pOH at 50 degrees Celsius? Now, anyone who was not paying attention to all of these previous examples might say 14 minus 6.6, 7.4, but of course that's incorrect. In pure water, pH equals pOH, so the pOH would also be 6.6. All right, I'm going to show you one more practice problem. And then after this practice problem, I'm going to go to an AP practice problem that I will give you for homework. So this problem will be the last problem that we do together in this lesson. And then I will show you an AP problem on the screen. When I get to that final problem for homework, you can just take a screenshot or pause the video. And then in tomorrow's lesson, you'll be able to see the answer to that question. Let's go ahead and finish up with this particular practice problem. All right, a sample of pure water has a pH of 7.39. So what is the value of the pOH at this temperature? And the answer is 7.39. What is the value of the H3O plus in this sample? You have to do 10 raised to the minus something, in this case, 10 raised to the minus 7.39. If you do that on your calculator, you get 4.1 times 10 to the negative 8. That's the number of moles per liter for both hydronium and hydroxide. And if you multiply that number by itself, in other words, if you square it, that will give you the value of Kw. In this case, it is not 10 to the negative 14. It happens to be 1.7 times 10 to the negative 15 if you do that math on your calculator. So is this hot water or cold water? Well, if we know that the reaction is endothermic from left to right, then this would represent cold water because the pH was actually higher than 7. All right, I'm going to move on to a summary and that final AP practice question. So in today's lesson, we talked about the definition of pH and pOH. We talked about the fact that H plus and H3O plus are used interchangeably. We talked about what it looks like in pure water and how the Kw is affected by a change in temperature. So I'm now going to switch to your homework problem. This homework problem is going to take up 2 different slides. So if you are going to take a screenshot, it's going to be more than just this particular screen. And so this particular AP exam practice question will remain on the screen, or you can hit pause and you can write this down. So we have this particular question. Answer the following questions related to the chemistry of HI, hydrogen iodide. A solution of aqueous HI is added to a solution of methylamine, CH3NH2. An acid-base reaction takes place. All of the water is removed by evaporation, producing crystals of the ionic compound methylammonium iodide. In the reaction described above, methylamine and the methylammonium ion represent a conjugate acid-base pair. Does the methylamine behave as an acid or a base in this reaction? Justify your answer. Write the chemical formula, including the correct charge for the methylammonium ion. Then, related to HI, we have a chemical equilibrium involving HI, and the reaction has an equilibrium constant of 790 at 298 Kelvin and 55 at 700 Kelvin. So based on the information shown above, is the forward reaction from left to right classified as an endothermic process or as an exothermic process? So again, if you're watching this video live, you can always pause the video. If you're watching it later on demand, these questions, these 2 questions will be what will be talked about in tomorrow's lesson. So this brings us to the end of this lesson on topic 8.1. I want to say thank you to everyone for watching. We hope that you will join us again for the entire series of AP Chemistry questions. Again, be sure to complete that practice question and we'll review the answer in the next lesson. So again, thanks everyone for watching.